All right. Hello, everyone. So this week we have actually started with representations, matrix representations. I have introduced some of the basic concepts. All of these concepts are going to be in the notes that I'm going to provide. So right now I'm just looking at if I need to change something in the notes actually, but I'm going to provide them. So these are not going to be in the exam. Just sorry about this. Let me correct this. So it is possible that some parts of this can be in the exam, but I'm going to. I didn't make up my mind yet, so I'm going to make an announcement within this week about what's going to be included in the exam. Right? So the exam will be on May 2. Right, I'll just write this thing down. Right, the exam. May 2, Tuesday, right? And it is between 8, or it's just started 6 o'clock, and then well, it will end up at 8. Okay. So, as I said, I mean, some initial portions of this representation topic might be included or may not. Okay. So let's remember this. First of all, G is a group. It can be any group actually. And A is a function from the group to, well, let's say n by n matrices in here. That is a function like that. So every element of the group is somehow represented by some kind of a matrix, right? So we call this matrix as A of G, for example, if the element is G. So if the product of the matrices satisfy the same product rule for the group elements, then we call this A as the representation. Right? So if this is the case for all G and H within the group, then A is called a matrix representation, but I'm just going to call it representation here. I mean, probably in mathematics, there are other kinds of representations as well. But in physics, I mean, these are the things that we are interested in. So there are like operator representations as well, but we can express operators in some kind of a matrix form too. So as a result, they are also matrix representations as well, right? So for us, for physicists, all possible representations of groups will be like that. Okay? So by this, I don't mean that this representation is faithful, right? Different group elements are represented by different matrices. I don't mean that. Sometimes there are like trivial representation. So trivial representation. For example, let's just call this by T, for example. So in that case, from G to 1 by 1 matrices, where each element is equal to 1. So in that case, it's easy to check that this relationship is satisfied. Okay? So 1 by 1 matrices, probably I said this before, I don't distinguish them from numbers. So you can think of this one-dimensional representations as just functions from the group into the complex numbers, right? So let's just keep this in mind. So that's for all G. So this trivial representation is actually quite important because it actually, whatever that representation means, it implies that something actually doesn't change under this symmetry transformation. So it's kind of expresses some kind of a symmetric object actually. So because of that, it is important. So don't take this too lightly actually. So in any case, so that's one of the things. So that's our definition, right? So just keep in mind that in the definition, the order is important. So if I don't know, I mean, let's just call this like V of G as the transpose of A, where A is a representation, let's say. So in that case, you can check that BG, BH product is equal to BHG, right? And in general, since this relationship is not satisfied in that order, Well, so this implies that B is not a representation. So this order is actually important. Let's just keep this in mind. So for non-abelian groups, for example, if A is a representation, then the transpose of A is not a representation in general. There are some other examples of similar kind as well. So in any case, here we would like to actually choose these matrices to be invertible as well. So therefore, the identity, for example, is expressed by an identity matrix. So we actually want these matrices to be invertible. So I can actually express this as the general linear group, right, of n by n matrices. Okay, so as a result, in that case, this is basically a homomorphism. And some of the things that we have said about homomorphisms between two groups is going to be valid also in here. So if A is a representation, let's say GL and C, let's say, right? So is a representation. Then, first of all, the identity is represented by n identity matrix, which is a matrix where all entries on the diagonal are equal to 1 and all off-diagonal entries are equal to 0. So I don't know how to write this thing down. So that's the identity matrix. Okay. In general, I mean, a homomorphism maps the identity element of one group to the identity element of the other group. Second thing is this, if A maps an element to a certain matrix, then A maps the inverse to the inverse matrix. I can actually write it down like that. So that's one of the rules that we actually use a lot. But if you want to read it in an alternative way, it actually goes like that. If G is represented by a matrix M, then inverse of G is represented by the inverse of that matrix. Okay. So I think that's it. Right? We have some other ways of actually producing some matrix, some representations. So let's say that if AB are, let's say, I don't know, sorry about that. I'm going to take the dimensions different. So if AB are representations of a group, then the direct sum of these, basically I'm going to use this notation, A plus B is defined as follows. So I'm going to do it like that. So what we do is like we just define these matrices for the representation C in this form. First of all, we take the matrix A of G, all right? So, I mean, this is probably an n by n matrix, let's say, right? So therefore, this is an n by n matrix. So I'm going to place this in some block in here, and then I'm going to place the matrix B on some other block in here. So this is going to be a block of a different size. So that's m by n probably. In any case, so we basically build the bigger matrix like that. So let me try to draw it like that. And then I insert in all the zeros for all the other blocks in here. Okay. So as a result, this is a bigger matrix where the size is m plus m by m plus n plus n, right? So if A is, sorry, let's say if A is n dimensional and B is m dimensional, then C is n plus m dimensional. So C is a bigger dimensional representation. So by using this method, we can build bigger representations from known representations. Okay, so this is something that we are going to use a lot. So as a result, I'm going to use this shorthand notation actually in here. So instead of writing these zero matrices or trying to express them, I'm going to use this kind of a notation, right? B of G in here. So whenever I don't write anything in here, for example, just assume that there's a zero block in here. So that's a zero block. Okay, just keep this in mind. But since I don't want to spend too much time in writing these kind of things, just keep this in mind. So basically, these are the diagonal entries are actually blocks of submatrices, and these are square blocks actually. So both of them are square, but yeah, I don't want to actually express them like that. So when time comes, sometimes I'm going to insert something in here, in which case sometimes I may actually divide them by lines as well. But I'll try to use this kind of a notation. Okay. Another thing is that think about this. A plus B is not the same thing as B plus A, right? So as a result, if I have like, I don't know, B of G in here and A of G in here, I'm going to get another representation in here. So let's just call this like C prime G. By changing the order, if these are different representations, I get a different representation. So in that case, C prime would be equal to B plus A. Okay. Let's just keep this in mind. So that's one thing in here. And sometimes we can actually use this kind of situations like, I don't know, if I have like small representations like A of G, I can use these blocks many times. Let's say B of G, B of G, and B of G in here. So that's a nice example. So I don't know, let's say this is D of G. So that's also a representation. There are too many zero blocks in here that I don't have time to write down. So in any case, so that's basically D is a direct sum of 2 A's and 3 B's, right? Normally I should write this thing down like that. But sometimes this is actually quite tiring, and so as a result, we would like to do a short notation. So in those kind of cases, instead of A plus A, we are just going to write 2 times A. So this actually means that the block A appears twice, right? It doesn't mean that I'm multiplying these matrices by 2. We don't. It just tells us that there are 2 copies in there. Right? Just keep this in mind. So that's actually a shorthand notation. So another way of actually obtaining different matrices is the similarity transformation. So similarity transformation of representations. Okay, so if I have A is a representation, let's say, and let's say S is an invertible matrix. In that case, I define A prime as, let's say, is defined as A prime of G is equal to S A of G S inverse, right? So in that case, you can show that A prime is also a representation. So by a similarity transformation, I can obtain the same, a similar representation. So this is basically for all G, all right? So it's the same S matrix, but for all G. You can easily show that this is the case, but I don't want to go into the details. Now, what's important in here is that similarity transformation has a special meaning for us. It's actually the point of view that these matrices are actually can be considered as transformations of vectors. This is just a, I don't know, if you apply this, for example, matrix to a vector, you get a different vector. So let's just call this as V prime, or I don't know, W or something like that, right? So I can think of this A of G as a transformation, a linear map from a vector space to itself. So V in here is the vector space of n by 1 column vectors with complex entries. So in that case, well, I can think of it as a transformation, but we usually, let's think of it like this. For example, E1, I mean, we have something called the standard basis, right? So these are actually the vectors like that, right? So E2 is, for example, the vector where the second entry is equal to 1 and all other entries is equal to 0. Right? So I'm going to use E for the standard basis. So these are also vectors which are perpendicular to each other. So that's called the standard basis. Okay, I can think of this each of A of G as applied on these vectors. This is actually going to produce some kind of a number of terms in here. So we write down these terms as like AJI. I think I'm going to write AJI. Yeah, I'll write it down like it, all right? EJ in here. Okay. So as a result, I can describe this transformation like that. So that transformation applied to one of the basis vectors gives you some set of coefficients with these. It's just a linear combination of the same things in here. So these things, these are basically the coefficients in here are the matrix elements of these matrices. So essentially, I mean, I can think of these things as transformations, and the matrix itself is just the matrix of these entries that appear in this expression, right? So that's actually a nice point of view. So this entry would be A11, this entry would be A1 through G, and so on. Okay. In any case, so these coefficients only appear when I use the standard basis, but I can use other bases as well. If you use another basis, then you get a different expression, right? So it's something like that. If let's write it down like A1 to AN is another basis, right? In that case, A of G applied on AI can be written as this. So there are some matrices in here. So I'm just going to call this as BJI. That also depends on G as well, AJ, let's say, right? So I'm putting the vector signs over the vectors in here. So there are new coefficients appear in here. So these new coefficients actually form another matrix in here, right? So that's B11G and B12G and so on. So you also have a square matrix in here if you use a different basis. Okay. So we say that, well, there is an operator in here. There is a transformation A of G. And this transformation has different matrix representations. So in one basis, the corresponding matrix looks like that. In another basis, the corresponding matrix looks like that, right? So in any case, the similarity transformation is basically the relationship between these two. So B of G in here is equal to SA of G S inverse. You can show that this is really the case, where S is the basis change matrix, which is basically expansion of these basis vectors in terms of the other basis vectors, right? So these are basically the coefficients that appear in this basis change operation. So you can understand the similarity transformation like that. Okay. So in that case, although you're actually expressing something with a different matrix, but it's essentially the same operator, right? So as a result, we would like to view these similar matrices as essentially the same operators, okay, from this abstract point of view. Okay, so as a result, we have to understand this this transformation like that. If A is a representation, a similarity transform of that representation is essentially the same representation, but they appear with different matrices, okay? So this point of view is kind of simplifies some of the features. So for that reason, we just define some equivalence of the representation. So if, let's say, I'm going to write C and D are representations, then, well, sorry about that. We say C is equivalent to D if there is a similarity transform such that, well, C of G is equal to S E of G S inverse for all G. Okay, so in that case, I mean, the notation for that, the equivalence is this 3 lines. Right? So I'm going to use this notation for expressing the equivalence. Okay, so the idea in here is that basically the equivalent representations are really the same, but they are expressed by using different bases. So that's something that we have to keep in mind, because in most of the situations, we would like to find, for a given representation, we would like to find an equivalent representation, which is basically as a matrix. It looks very simple, right? So we are just going to do this by finding another basis, essentially. So there are like systematic procedures for doing this. Okay. So I didn't say this before. So the direct sum, for example, if you in the direct sum, if you just change the order, of course, you get a different matrix. They are not equal matrices, obviously, most of the time, but they are equivalent, right? So they are going to be equivalent to each other. So most of the time, I will be using this equivalence relationship, actually. So as a result, I mean, there are places where you have to be careful about this. So most of the time, I won't be talking about the equality of the 2 representations. I'll be talking about the equivalence of 2 representations. Because there are some systematic ways that we can actually do this. We can actually understand under which conditions can I say 2 representations are equivalent. Okay? They are very nice tools, actually. In any case, so the idea in here is this idea, right? Given a representation A, right, find a similarity transformation so that, right, A can be written as, it's not A, but it's a similarity transformation to something else. Right? Similarity transformation to a direct sum of simpler representations. Okay. So A is basically given A. I would like to transform it to, and by a similarity transformation, let's say similarity, to a matrix where this matrix is in the block diagonal form. So as a result, there are like some fundamental matrices in here. I don't know, U1, let's say, and then U2 appearing 3 times, and then U3 appearing like that. So we would like to basically express any given representation as a direct sum of these somewhat simpler representations, right? That's basically what we are going to do. Okay, but we have to introduce some concepts to be able to do this. So first of all, if I can do this for a given representation, then we just call this representation as decomposable, right? Or completely reducible. So I can actually express it in terms of smaller ones, things like that. So, but I need to define them in a careful way. Okay, so there are a few concepts in here. Right? A is, oh, sorry about that. I need to talk about this. So V is the vector space of n by n by 1 matrices, right? Column vectors. Okay, so the dimension of that vector space is equal to n. Just keep this in mind. W is a subspace of V. So you know from linear algebra what subspace is, right? So there's a bigger space in here. W is just a subspace inside. It's a subspace if the sum of two vectors is inside in here. I mean, all the linear combinations of vectors inside W is also a linear combination. So in particular, this actually tells you that the zero vector is also within this subspace as well. Right? So we have a definition in here. Sorry, we have these two special subspaces. So zero, so W equals 0 is, well, is the zero space, right? Is the zero space. So it's the most boring subspace, actually. It just contains the zero vector in it. So it just satisfies the definition. So the full space is also is a subspace. So these two special subspaces are called the trivial ones. These are trivial subspaces. Okay. If a subspace is non-trivial, right? W is non-trivial. If it's not trivial, obviously. So if it is not the zero space, not the full space, right? But I can express this as a condition on the dimensions. So the dimension of the zero space is 0. So that's the only subspace with dimension 0. So if the dimension of the subspace is bigger than or equal to 1, it is non-trivial. But it should also be smaller than the subspace of the full space, actually. Okay, so all non-trivial subspaces basically satisfy that condition, right? So there's actually a definition expressed in terms of the subspaces. Sorry, it's a subspace. So as a result, I just wanted to remind you this. So A is a representation of some group G. Okay, we say that a subspace W is called an invariant subspace. Invariant subspace of the representation, actually, is called an invariant subspace of A if A transpose transforms all vectors in W to vectors in W. I mean, sorry, A of G, actually, for all possible A of G. So let's say it like this, for any vector that I choose in W, and let me write any in here, for any vector I choose in W, and any group element, right? So A of G is the corresponding representation matrix. Consider the transformation. So this matrix applied on W produces another matrix. If this is in the subspace, is in still the same subspace, then we say that, well, W is an invariant subspace. Okay, so that's basically the statement in here. Some people actually write it down like that. A of G applied on the subspace itself is an within that subspace. It's a subset of that subspace. Then we say that this is W is an invariant subspace. Okay, for all G. In any case, so the definition is that the A is called reducible if A has a non-trivial invariant subspace. Okay. So that's the definition of the concept of the representation being reducible, right? So if A is not reducible, I mean, well, it's not reducible, so it doesn't have any non-trivial invariant subspaces. So if A is not reducible, then A is called an irreducible representation. All right. So this is a term that I'm going to use a lot. So in writing this thing down, I'm going to just use the shortened form irrep, all right? Because this is kind of easier actually, especially in class and so it's a term that we need to use a lot, but it's actually two long words actually. So instead of irreducible representation, I'm going to write irrep. All right, just keep this in mind. So we'll basically show that these are our fundamental representations, basically. Yeah, whatever. Let me just try to explain what that thing means. So first of all, in terms of matrices, it basically goes like this. So if A is reducible, let's say, if A is reducible and W is the non-trivial, obviously, non-trivial invariant subspace. Okay. So what we do is this. So W is a subspace in here. There is a bigger space, which is B, right? We choose a basis for W, right? Choose a basis. I'm going to call the vectors A1 to AN for W. Next, so that's the first step. The second step is, I also want to choose a basis for the full space as well. So what I do is like, I just complete this to a basis, right? So the first M vectors are within W. The remaining vectors will be outside W, right? So complete this to a basis for the full space by adding vectors AN plus 1 ... AN. So we just find new vectors. Okay. So as a result, we have like two bases, but one actually contains the other one, right? So let's say it like this: A1 to AN. Let me put the arrow signs in here. AN plus 1. So we have like these n vectors in here. This part is this part basically spans the subspace. This part spans the full space, right? So that's the spans the full space. It turns out that if you express A in this basis, right? If A of G is expressed in this basis, A1 to AN basis, we get some kind of a matrix, obviously. So let's just remember that this is just a similarity transformation. What happens is that for the first M vectors, the representation matrices look like that. So the first M entries are probably non-zero, but the remaining entries are equal to 0 because basically the first column is basically A of G applied on A1 vector. And since this is a vector in the subspace, this vector is just a linear combination of the first M vectors. So as a result, the first M numbers in here are actually equal to non-zero. So the idea in here is that the first column of that matrix is actually the operator applied on the first unit vector. Okay, and similarly for the second unit vector. So as a result, I'm assuming that there are like m is equal to 4 in here. So there are like first four, for the first 4 vectors, we will have the first 4 entries to be non-zero. All the entries will be 0. So as a result, we have a square block in here. Right? For the other ones, for the fifth one, through the other ones, it is possible that all entries are equal to non-zero, right? So as a result, we have some non-zero entries in here. So let's not just write this thing down like that, but it appears that I have some kind of a block in here. So I'm going to call this, I don't know, let's say P of G. This is a square block, and there's a square block also in here, probably bigger. And there's another block in here, so I'm going to call this as R of G, for example. But 0 is in here, right? So a matrix is reducible if you can make one of these subblocks, off-diagonal subblocks, but not both of them. One of the off-diagonal subblocks to be equal to 0. All right? So in general, for matrices, A is reducible means it's the same thing as saying that there's some kind of a similarity transformation in here where the matrix is basically equal to that, let's say, upper triangular block, right? Where this part is equal to 0. Okay. On the other hand, we say that, well, that's a new definition. A is completely reducible. This is the same thing as saying that a matrix by a similarity transformation can be converted into a form where we have a block in here, another square block in here. So both of these are diagonal blocks. They are all diagonal blocks are square. And then we have an off-diagonal block in here, but that's a 0 matrix, and that's a 0 matrix as well. Well, that's a 0, right? So if I can make both of the off-diagonal blocks 0 matrices, then we say that the representation is completely reducible. If you can make only one of them, in which case you just say that it is reducible, but probably not completely reducible. Okay, so there's an alternative way of saying this. We actually call this as decomposable. Okay. In any case, for a given representation, if I want to express this in a representation as a direct sum of smaller representations, then this is the complete reducible to feature is what I want, right? Okay, so this part is a little bit complicated. For a general group, there are lots of groups, right? Some of these also appear in symmetric groups in physics as well, like the translation group and things like that. There are finite groups, there are Lie groups, there are infinite groups, infinite discrete groups, infinite continuous groups, and things like that. So we are kind of interested in the representation theory of all of them. There are examples of groups where there are representations which are reducible, but not completely reducible. So we can see lots of examples of representations of that kind. Okay, and they are not simplified enough, actually. So the representation theory for such groups is actually quite difficult. So there are these kind of complications, but in this course, we will just look at finite symmetric groups. Okay. If G is a finite group means, well, the number of elements within the group is not infinite, right? This is the mathematician's notation. Yeah, well, let's just write this thing down. I mean, it's just a number. The order of the group is a number. Then there are many things in here. So in that case, reducible implies completely reducible. So a representation is reducible if and only if it's completely reducible. let's just write this thing down, right? I mean, for a finite group, reducible and completely reducible is the same thing. So somehow, if it is reducible, then it's completely reducible. So as a result, for finite groups, we are actually looking at these properties of reducibility. Okay, so the smallest possible representations are the irreducible representations. So that's why we are interested in them, because the irreducible representations are the building blocks of the bigger representations. So that's the first thing. Second thing is that, every representation is similar to, it's equivalent, right? So that's the correct word, sorry. By a similarity transformation, you can convert it to, so it's equivalent to a unitary representation. Okay, so from this point on, I'll be interested only in finite groups. Okay, so the first statement that I'm going to show I have shown in class, but I'm going to also kind of start showing it, but I'll show what the idea is. I'm going to show this thing in here. So for a given representation, I can actually find a similarity transformation that converts this to a unitary representation. So that's the first thing. And then I also kind of argued this. For a finite group, if a representation is reducible, it is really completely reducible. You can actually show it with each other. However, this is the part where this course becomes much more mathematical, all right? So there are places where we can actually kind of lose all the details in here because we are somehow, I mean, we actually go into the details of the mathematical proofs, right? In any case, so I'm going to start with 2 in here. So the proof is something like that, okay? So G is a finite group, right? So let's say that let A be a representation, B and let's say n by n representation. Should I actually give the dimension? It's not really important, but if I want to mention dimension somewhere, then I need to do this. So what we do is we just define a matrix M in here, which is obtained by sum over A dagger G and multiplied with AG. Is there any physical meaning to that? No, it doesn't have. But it's just that it appears to be a nice matrix, and this matrix satisfies some important property, which we actually use again and again for some other proofs that we are going to encounter later. Right. So as a result, this is important, right? So that's basically for all representation matrices, I'm going to express this product and then sum all such products over all of the group elements. So that summation is actually a summation over all group elements, right? So in any case, so if I multiply this matrix with another representation, I mean, let's say that H is an element of the group. If I multiply this, then I can express this as a summation like that. So that's A dagger G, AG multiplied with AH. So let me make this a little bit faster in here. So we notice that this is equal to AGH. Okay. We change the summation to G prime. So I just call the inside, right, as G times H. So as a result, G in here is equal to G prime times H inverse. So as a result, I can write this thing down as A dagger of G prime times H inverse multiplied with A of G prime. Okay. So this is basically a change of dummy variable. So instead of using a summation over G, I'm using a summation over G prime. Okay. But the fact that, well, we are actually using the rearrangement lemma in here. Rearrangement lemma. Okay. basically, if I take all the group elements and multiply them from right by a fixed element like H, then I get the same elements of the group, but in a different order. Okay. So as a result, the summation over G prime is actually sums over all of the group elements, but it does it in an opposite way, in a different order, perhaps. But the different order doesn't change anything because it's just a summation. Okay? So in any case, so this expression is also a sum over the group. G prime runs over all group elements. In any case, so this expression is the Hermitian conjugate of a G prime H inverse. But I can write this thing down like that, the Hermitian conjugate of that. But the Hermitian conjugate changes the orders of the elements. So therefore, I can write this thing down like this. And so therefore, I can write this thing down as A dagger H inverse, and then sum over G prime of A dagger G prime, A G prime. In any case, this is summed over a different dummy variable, but it's the same thing as in the definition of M. So therefore, this is basically M. Okay. So what we have shown is that M multiplied with AH is equal to A dagger H inverse M. All right, so that's our first relationship. Second relationship actually tells you that, so this part is a little bit more technical. So first of all, M is Hermitian. It is invertible, and it has positive eigenvalues. So it's kind of easier to show that it has positive eigenvalues, but I don't want to provide the details in here. So if it doesn't have any zero eigenvalue, that implies that it is invertible. In any case, so I can therefore do a similarity transformation. So I can write M as to a diagonal form. So I can write M as some matrix V multiplied with a diagonal matrix. So that's a diagonal matrix. And then V inverse. Right? So that's a diagonal matrix. Okay. So since M is Hermitian, I can choose this similarity transformation to be a unitary similarity transformation. That's also kind of important as well. In any case, so in which case this V inverse is the same thing as V dagger. Okay, but this is a similarity transformation. The diagonal entries are basically the eigenvalues, but since they are positive eigenvalues, I can actually take their square roots. So I just define S as a matrix where it's the same form again, but instead of this diagonal in here, I use another diagonal matrix where, but the diagonal entries are the square roots of the eigenvalues. You can show that in that case, S squared is equal to M, but S is Hermitian. Invertible. It also has positive eigenvalues as well. We just call this S as the square root of M, right? S is called square root of M, right? There's not much left in here, but I mean, this is basically the property that we need to use in here. Okay. So let me quickly transform this. So therefore, I can write this thing down as like S squared AH is equal to A dagger H inverse S squared in here. What I do is like I just multiply this expression by the inverse of S from left and right. And in which case, the left-hand side is basically SAAH S inverse. And the right-hand side is S inverse A dagger H inverse S. Okay. I can easily show, you can easily see that this is the Hermitian conjugate of this expression in here. So as a result, what we do is we just define a new matrix U of G as, or U of H as this similarity transform S inverse. In that case, this equation looks like that, right? U of H is equal to U dagger of H inverse. instead of H, I can write G inverse in here. So therefore, U of G inverse is equal to U dagger of G. But since this is a representation, the inverse of the representation matrix is the inverse of the matrix. Sorry, inverse representation of the inverse of element is the inverse of the representation matrix. So whatever. So that's basically equal to its Hermitian conjugate. So this implies that U of G is unitary. Okay. So this, I mean, this is basically the end of the proof in here. So let's come back to the statement in here. So basically, we have shown that, right? If the group is a finite group, every representation is equivalent to a unitary representation. Here, the finiteness is actually used in this summation in here. If the group is finite, we have a finite matrix in here. But if this is an infinite group, then, well, we won't have this. And so as a result, this proof is not going to work. Okay? So this is the first step. From here, we can actually show the other one quite easily. Okay, so I'm not going to do this, but it is actually done in the notes. So I'm not going to go into that much detail. But next week, I'm going to do some kind of a summary that explains this as well. Okay, so let me stop here. Stop here. How do I stop? Okay, I'm going to stop sharing first and then stop the recording.